Dirk's going to fall asleep before we even started. That's not a good sign. That's not a good sign. Good evening, all. Hope you're all well. Evening, Miss Robertson. In the usual cupboard under the stairs. Oh, hi there, Kate. Kate's got a camera. I didn't realise you've got a camera now, Kate. That's great to see you. Great to see you. Good. I hope everybody's had a good week. Still a distinct lack of skies around my way. I don't know about anybody else, but there we go. There we go. Right. Let me. Evening, Norman. Just seeing you come online there. I think everybody's in now from the waiting room. Are they, Grant?
Yeah, I think so. There's a couple of people just joining late doors, but
right. In that case, then we will. Oh, so many screens.
I think the other issue we have, Dirk, is quite a few people had already seen this talk when we posted up about it. So I think you've obviously done it so many times now.
Right, we will kick off and we will make a start. Good evening, everyone. So week 35, I think, barring the breaks we had for Christmas, which is really good. And again, really good to see you all. I hope you are all well. Grant, what's the recording for tonight?
Yep. So Dirk doesn't mind us recording and making it available as we see fit. So. We will. Thank you very much, Dirk.
Good, excellent, excellent. And as usual, if you've got any questions, put them in the chat, and we'll have a Q&A session towards the end. At the end, obviously, not towards the end. We can have the Q&A session and then the conclusion. That might be a bit more interesting to do it that way. Oh, it's been one of those weekends. What can I say? What can I say? Excellent. Right, I'm going to do the introduction and then shut up. So tonight we are really pleased to have with us Dr. Dirk Froebrich, and we did check pronunciation just before we came on air, and that's as good as I'm going to get, I'm afraid. So tonight, Dirk is going to be talking to us about HOYS citizen science. We've had a few citizen science talks in the past, and this is building on that and another one of those. So this is going to give us a brief overview of how stars and planets are forming and how this relates to the science goals of HOYS. And hopefully Dirk's going to share some recent results from the project and explain how we as astronomers can participate. So Dirk, we look forward to this. So I'm going to stop sharing, he says, and then you can share yours.
Okay, let's try this.
Perfect, we can see that, thank you.
Get my laser pointer, yay.
Oh, that's very clever.
Very good.
Standard PowerPoint functionality. Okay. So, good evening, everybody, and thank you for inviting me to give a talk today about our citizen science project called HOYS. And it's me as the PI. So my name is Dr. Dirk Froebrich from the University of Kent, and I have a co-PI or co-science lead, Dr. Alexander Scholz, who is running the big telescope in St. Andrews University, so the biggest still working or currently working optical telescope in the UK. He is running that in St. Andrews. And what the acronym actually stands for is Hunting Outbursting Young Stars. And in the introduction, it should be clear after that what that actually means, what we're trying to do. And in the talk, what I will do is I'll give you a brief basic overview about star formation, planet formation, and in particular the bits that you will kind of need to understand some of the results I'm going to show you, and which will be in the second half of the talk. And I will also, of course, before that, explain why we do this as citizen science, but in a very different way to many of the other citizen science projects that you will find. So the typical Galaxy Zoo type citizen science project is you will kind of be mistreated as data monkeys, where you look at things and you classify things, Our approach to citizen science is that the citizen scientists actually deliver the data. We will then do the analysis. We also have started to trying to educate people in doing their own analysis of our data, which is completely public once you send it to us, and do your own little research if you really want to do this. And towards the end, I will tell you a little bit how you can actually participate if you want to help gather data for our project. So, okay, let's get started. You are number 49 in terms of the number of talks we've now been given over the last 2.5 years on this project. So on the left, there are all the other 48 audiences. The last 6, I think, we had to do online, but all the other ones, I've been there in person, so I've driven quite a large distance now to get to all the talks. I've spoken to 1,600 people, 6 cats and 2 dogs over the time. And in a couple of weeks, we have our kind of anniversary talk, number 50, which hopefully will get a good audience as well. But let's actually start with the content of the talk. A very, very basic overview how stars and planets are forming. So very, very briefly, to give you an idea of what we are trying to investigate. Stars form out of giant molecular clouds. So these are gas and dust clouds, which occupy about 1% of the volume in the midplane of any kind of normal spiral galaxy, including our own. But these clouds, they contain about half the mass of the galactic plane that is not in stars. So they're much denser than the surrounding material. They're made up of molecular hydrogen. That's where the name comes from. So about 3/4 of the mass are molecular hydrogen. The other quarter is helium, which doesn't do anything. It just sits there and increases the mass. And then you have about 1% of the mass, which is in dust grains, so tiny silicate and graphite grains, which are actually very important constituents, even if they just make up 1% of the mass. Because it's those dust grains which allow the cloud to get rid of its thermal energy, so allows the cloud to cool towards low enough temperatures for star formation to start. We're going to get to this in a second. And also these dust grains, they scatter light, in particular optical and ultraviolet light that is trying to penetrate these clouds. And we will see that on the next slide in a couple of minutes, how we can use this scattering to actually learn about the dust grains themselves. So in terms of their size, they're quite small. They're about only a micrometer in size. They're much smaller than the typical dust you find in your house. But they are basically the star, the building block of the planets that we will form around these young stars later on. But in these giant molecular clouds, basically once you have that, they typically weigh between 1 and maybe 10 or a couple of tens of millions of solar masses, so extremely massive entities. And the only thing you need in these clouds, in principle, in terms of physics, to make stars is gravitational force. Because to form a star, you need to somehow accumulate material into a star, and basically in a very small area, a point, so to speak, compared to the size of those clouds. And gravity is the only force who can really do that, accumulate the material in a particular area. Now, there's a lot of other forces acting in those clouds. So I mentioned one already. These are the thermal pressure. So the clouds have a temperature, which means the individual gas particles, they move about. And if you increase the temperature, the gas particles are going to move quicker. This is basically what's called the thermal pressure, which tries to disperse the cloud. So the gas particles, if you heat the gas, they tend to try to escape the clouds. Then you have turbulent motion. So there's other forces which stir up the material in these clouds, which are in part external and part internal to the cloud, which again just move the particles in the clouds, or try to give them more energy, which will try to make them escape. Then there are magnetic fields, and we have charged particles in those clouds, and again, these magnetic fields will prevent the collapse of parts of the cloud into stars. And then there's of course rotation, right? If you rotate something very fast, you get centrifugal forces, and that again acts against gravity. But every now and again in these clouds, you get so-called dense cores, which have a density or mass that is high enough that gravity actually becomes the dominant force in that region, and that will cause what we call the gravitational collapse. So the star or the material in that region will start falling towards a central point, because gravity is basically winning over all the other forces, and hence the material starts to fall to a central point. And what happens very, very quickly is all these cores will rotate a tiny, tiny bit. So there's basically no scenario you can think of that there isn't any kind of net rotation in these dense cores. And very quickly we get what we in physics call the angular momentum conservation problem. So angular momentum is quite a difficult concept to understand, but you could just go and watch figure skating on TV, where the figure skaters basically stand on the ice, have the arms stretched out, and they rotate about their axes. And what they do is they pull the arms in, and the rotation is spinning up. That's exactly the same what will happen in those clouds. So there's a little bit of rotation, and gravity is pulling the material towards the center, so towards the rotational axis, and hence the cloud will simply rotate faster and faster and faster. And what you then get is in the equatorial plane of that rotation, you get a centrifugal force, which very, very quickly becomes big enough to compete with the gravitational attraction, and it will stop the collapse of the cloud in the equatorial plane of your rotating object. So along the rotation axis, there is no centrifugal force, because the object, let's say, goes around this way. The centrifugal force acts in the equatorial plane or perpendicular to the rotation axis. So along the rotation axis, material can still fall towards the center. And what happens hence is you form this kind of donut-shaped accretion disk around the central object, where gravity has kind of accumulated all the material. So that central object is what will later be the star. So once it gets dense enough to start the fusion process, that will be the star. And it's this accretion disk which we are really investigating in our work. So once you have that accretion disk, the material can't really fall straight onto the star anymore. It will basically, from the cloud that is still around, it will settle on the outer edge of the disk, and then slowly move through the disk all the way to the inner edge, and then be dropped onto the star in the actual mass accretion process onto the star. And this is one of the things that we're trying to investigate, basically, how fast does the mass move through that disk and drop onto the central star. Because once you know that, you know exactly basically how long does it take to make a star like that. Sometimes there's a lot of material that falls at the same time onto the star, so that frees a lot of energy, the gravitational potential energy from that material, and increases the brightness of the star by a very large amount. These are these outbursts that we're trying to find, which are mentioned in the acronym of the project. And what they do is they heat the material in the disk. So the disk material is basically made up of the same stuff that the molecular clouds are, right? So molecular hydrogen and dust grains. And if you heat that up, you change the chemistry of that material. So the dust grains are silicates and graphites, and there's all sorts of trace elements, all sorts of carbon, oxygen, nitrogen, sulfur, whatever you want, is in this disk material. And it's out of that material that you form the planets, right? The material that's not falling onto the star, this will over time grow from these micrometer-sized dust grains. They will start sticking together, form larger and larger objects like pebbles, boulders, and so forth, and eventually they become massive enough to start we accrete material out of the disk and start to form planets over time. And what we basically try to understand is that mass accretion process to see how often does the disk get heated to very, very high temperatures. This heat will actually evaporate some of the dust grains and stop the planet formation, at least in the inner parts of the disk. And also, how does that disk really look like? Because the way the mass basically accretes onto the star, we can determine that if we know how the disk really looks like on very small scales around the star. So this is what we're trying to investigate. And this is how basically the whole process works. Gravity wins in those giant molecular clouds. You get this initial symmetric collapse to form that central object. This only takes less than 500,000 years. So this is an extremely fast process. And then very quickly, even after about 10,000 years, you have that accretion disk around, which then drip feeds the remainder of the material onto the star and forms the planets. So these disks, they live about 10 million years or so, give or take a few. And it's in that time where the cores of the planets are really forming. So it's an extremely fast process in terms of astronomical timescales. So within 500,000 years, you've accumulated literally all the mass in a central object. And then within 10 million years, you formed all the cores of the planetary systems around them. And this is what we will try to study. And in particular, the very inner parts of these disks, that's where the terrestrial planets really form, the planets like the Earth. So we don't really trying to investigate how Jupiter forms. That's much further out, several astronomical units away from the star. We are really interested how the rocky planets form, things like the Earth, Mars, and Venus. Because these are honestly the planets you can live on. You can't really live on Jupiter, so I'm not really interested in that. So that's basically what we're trying to achieve with this project. So let's have one look at these dust particles in these clouds. So this is a picture on the left at optical wavelengths, so roughly naked eye wavelengths of a small cloud called B68. And what you can see is basically not much because the dust particles in that cloud, they really absorb and scatter mostly the light of all the stars behind that cloud, so we can't really see them. On the right is exactly the same picture, but at infrared wavelengths. And what you can see is you start to see the clouds actually shine through the clouds because the amount of scattering is lower at longer wavelengths. What that basically does is these dust particles, they will basically scatter light, which dims the light of the stars behind and also changes their color, because most of the blue light is scattered away, and what's left is basically the red light that is able to travel through those clouds. Schematically, you have your star here. You're sitting with your telescope on the right. You got your cloud with all these dust particles here, these small dust grains about 1 micrometer, and they like to scatter blue light, and they don't really like to scatter the red light. So what you see is the red light. And interestingly, if you know how the light or what the color of the star is that you're looking at, the light that you receive with your telescope, or the color of that light in particular, or what fraction is blue, what fraction is red, that can tell you about the size of these dust grains. So you can basically tell, are they like the interstellar dust grains? Do they have a size of about 1 micrometer, or are they bigger, i.e., if they start growing in a disk, for example, and you somehow look at light that goes through the disk from the star, then if the dust particles have started to stick together and have become much, much larger than 1 micrometer, so they will be much, much larger compared to the wavelengths of the light. Remember, green light is roughly 0.5 micrometer, so it's about the same size in its wavelengths as the normal interstellar dust grains. If you make these grains very, very large compared to the wavelengths, let's say a couple of centimeters, then they will still absorb and scatter some light, but they will do that in a completely independent of the wavelengths. So basically, if you got very large dust grains, the red and the blue light is scattered by the same amount, and the color of the star behind the cloud will not change. It will be dimmer, but it will have the same color. And that's basically helping us to see, have these disks already larger dust grains. So if you look at older objects with older disks, what you would expect is to see larger dust grains. So less change in color if you get occultations by disk material. This is one of the things we're trying to do. Okay. To summarize, what we're trying to do is really try to understand how terrestrial planets form. So what it means is we need to establish the detailed structure and the properties of the inner accretion disk, so the inner couple of astronomical units around the star, because that's where those planets are forming. So basically, if we know that structure in detail, you can feed that in a computer and let physics show you how the planets are forming. People already do that, but what they put in the computer is basically made up to give you the correct results, in the sense that they get the planets they want. So what we are trying to achieve is basically measuring the structure of these disks and the property of the material in there. And then you might ask, of course, now why hasn't anyone else done that? So let's basically see how, with current instrumentation, we can do this. Here are some pictures of some of these accretion disks taken with the Subaru telescope in Hawaii. So that's one of the biggest telescopes you can find on the ground. And the light of the star has been blocked out, so you can kind of see the disk emitting or scattering light. In particular, these are optical images. And you see there's some structure. So that there's some bits where it looks like some kind of streamer or structures here, almost spiral arm-like in some of them. And you can also see a scale bar. If you got a big screen, you might even be able to read the numbers. And the scale bar kind of tells you these are about 450 astronomical units, as this example. So you can see the size of these disks. They're bigger than our solar system, if you think it stops at Pluto. But there are a few hundred astronomical units across. But if you want to investigate the inner, let's say, 5 astronomical units, you got no hope of actually resolving anything from the ground, even with an 8-meter telescope. It's simply too small. These objects are too far away, and in particular, in the inner couple of astronomical units, the light from the star, which you need to block out, just ruin everything you're trying to do. Okay, so how can you do this much better? I always, people think throwing money at stuff typically works. So you can spend about $5 billion or so US dollars for the Hubble Space Telescope, shoot it up, spend another $500 million to repair it because you put the wrong mirror in, and then you point that at the closest young stars you can find and try to image those disks. And here are some examples where the young star is actually sitting where I've put the cursor. It's behind. We see the disk more or less perfectly edge on, so it blocks all the light from the star. There's no direct light coming through. And what you see is this kind of bowl-shaped feature here. And the reason for that is these disks are typically not flat like Saturn's rings. They're flared, which means if you go further away from the star, they get thicker. Basically what you see here is there's light from the central star. It's scattered off that curved surface of the disk on both sides towards the telescope, towards us. You can see that as these two bowls. And the color of that scattered light is the same as the color of the stars, roughly white a couple of thousand Kelvin, roughly like the sun in terms of its surface temperature. And then there, in green, there's a jet coming out along the rotational axis, which I typically don't really talk about because it's too complicated, and I spent 10 years of my life trying to understand them. But what you see is, again, a couple of other examples. Again, this disk edge on here, there's a scattered light. This disk is even more flared. You have another disk here, looks like a bit like an FUO. Again, you have these scale bars here for all objects, and these are now 200 astronomical units. So again, roughly the size of the solar system. But the detail you can see, even with Hubble, isn't really great. So the smallest detail you can see, even for the nearest objects in Taurus, which are about 300 light years away, the best detail you can resolve is about 35 astronomical units, right? That's all the way to Pluto. So studying the inner extraplanetary disk system doesn't really work, even with the Hubble Space Telescope. You can try to spend less money. You build the ALMA radio interferometry array in Chile. That's cheap. It's €1 billion. Again, you point that at the nearest stars and you look at the emission from the disks at millimeter wavelengths, because these disks are very cold, so they emit a lot of light, in particular the dust and the gas in it. And then you can get reasonably decent pictures compared to what you can do with Hubble. And then you see structures. There's rings and gaps of material. In these gaps, there might or might not be planets, which basically create these gaps by hoovering up all the material. And the resolution of ALMA is quite good compared to Hubble. So the detail you can resolve is about 5 astronomical units. So that is basically exactly the limit where we want to go below. So ALMA kind of stops there, even for the nearest young stars. That inner bit here, basically the size of the laser pointer, that's the bit we're trying to investigate, and that's the bit ALMA cannot resolve. You can spend even less money and build the very large telescope in Chile, which does optical imaging or optical near-infrared interferometry. And then again, you can kind of point this at the nearby young star forming regions to look at pictures of these disks. And this is now near infrared, so this is almost optical light. And again, they look like what you kind of expect already from Hubble, just with a bit more detail. Again, the stars are blocked out so they don't outshine the picture. And again, you see these flare disks here with some structure and reflected light and so forth. And if you're lucky, then you find an object like this, PDS-70, where this we think is an actually forming protoplanet in their disk, which is orbiting the star here, which is in the middle. There's a second planet hiding in that mess up here that people found once they made some better pictures than that first discovery picture of these objects. But again, the resolution of the VLT or the VLTI is exactly the same as the one from ALMA. So for the nearest young stars, it's about 5 astronomical units. So this planet here is very, very far away from the central star. So much further out than any planet that we have in our own solar system. But what about the very inner bits, right? So the inner fraction of an astronomical unit. This is not a picture we made. This is an artist impression how this could look like. So you got your forming star in the middle, you got the accretion disk around, and there's some structure. And everything in their disk, from the initial rotation, will orbit around the central star. Let's say this direction. So the stuff that is in front of the star in a picture or below will move to the right in an orbital way like this. And now, if you have a structure like this that might be sticking out, either because there's some magnetic fields here which do that, or there's a planet which throws material above the plane of the disk, that structure is going to move slowly to the right, and eventually some of that material might move in front of the star that we can observe. And what that material will do is it will dim the light of the star and it will make it redder. Right, if it moves on, the star will turn bright again, and then if there's a second part to that structure, again there will be a dimming event, and then things become brighter as well. And basically, that allows you, from measuring simply how bright the star is over time, to measure the size of these structures, because all you need to do is see for how long is the star dim. If you make a sensible assumption how far away these structures are from the center of the star, then you know the speed they are moving in front of the star. So the duration of this dimming event gives you the extent of or the size of the structure in the direction it's moving. And the resolution you can get from that is basically only limited by the size of your central star. The typical young star is the size of about 1% of the distance between the Earth and the Sun. So 1% of an astronomical unit. That's the resolution you can do. And this technique does not actually require you to do this for nearby objects. This works independent of how far away the star really is, as long as you can actually see it, if that's bright enough that you can actually get the light from the telescope. So that is quite good, because all these things with ALMA and the VLT, you can only do this at this resolution for the nearby stars. If you go to things which are a couple of thousand light years away, the resolution will drop quite significantly. So I always have this example now. How much better is this resolution compared to ALMA? So I think you all know how we measure angles, so I'm not going to go over that. But your naked eye basically has a resolution of 1 arc-minute on the sky, which means if you got a normal car and you park this 5 kilometers away, your naked eye can tell if it has 2 lights or 1. Your eye is actually quite good in terms of spatial resolution. The best ground-based telescopes, things like Subaru, the resolution is half an arc-second. So it's about 120 times better than your naked eye. You would think, a telescope like that would be a bit more better than your naked eye, but it actually isn't, because it's limited by the Earth's atmosphere. But in terms of the car, Subaru can tell from 600 kilometers away that a car has 2 lights or 1. So if you use the interferometry techniques like ALMA, VLT, the resolution is much better, 0.025 arc-seconds. You can park the car on the other side of the globe, 12,000 kilometers, but that's it. And that resolution corresponds to that Sun-Jupiter distance for the nearest young stars, those 5 astronomical units. Now, as I said, our technique is much better, because we can go down to 0.01 astronomical unit, not 5. And also, we can do this independent of the distance. So most of the targets we observe are at about 3,000 light years in distance. And so we can resolve 0.01 astronomical unit at a distance of 3,000 light years with this technique, reasonably easy. And in terms of the car, now that means you can park the car on Mars. That's the resolution. So that rover they accidentally kind of tried to shoot onto Mars a couple of years ago, we can see if it still has 2 lights on or just 1 in terms of the resolution, right? So that is basically the advantage of this photometric monitoring of young stars. Just looking simply how long are they dark from one of those occultation events to study the structure in great detail of these disks. And you can even zoom further in. These stars, as I said, they accrete material from the inner parts of the disks. The material just crashes onto the surface, creates shocks and hotspots. The stars also have dark spots, similar like the sunspots that we have. And of course, they rotate, right? So if you see these objects roughly edge on, sometimes, let's say if you have just 1 spot on the surface, the spot is at the front, you can see it. If it's a hot spot, the star will be brighter. If the spot rotates to the back, it disappears and the object gets fainter. So you can measure the rotation period of these things extremely quickly, but you can also basically measure the size of these spots and their temperature by monitoring how much does the brightness change as a function of wavelengths. So that's one of the other things we can do. So just to summarize that, we are monitoring brightness of young stars to get to resolve these disk structures down to the resolution limit or the size of the star, 0.01 AU, and we will measure these rotation periods as a byproduct, get a temperature and the size of these spots. We can measure their position and even how they move on the surface. So that is one of the research things we are trying to do with that data. And we want to do this with amateur kind of telescopes. So this is kind of a slightly larger one, but I'm convinced, and I know many of the amateurs have a bit more than what we have at the University of Kent, our 40-centimeter telescope there. But the project is basically designed to do this with small telescopes. And what we want to do is really monitoring our targets for 25 years with a high cadence, once or twice a day in every filter. Simply because material that moves at the inner part of these accretion disks, that will move more than the diameter of the star in about half a day. So that is a cadence that is quite helpful, and want to do this in all the possible optical filters that are standard. And all our targets, they're all young clusters of stars. So we get a lot of stars in the same picture. We don't do one star at a time. We do a couple of hundred, if not a couple of thousand in one picture. And we limit ourselves to about 25 regions so that we actually get really good data for all of those. But the targets that we've selected are basically cover the majority of the young stars and clusters in the Northern Hemisphere, which are within about 3,000 light years or so. Because they're so nearby, we can do this with these small telescopes. So you can easily see most of the young stars in those regions. And this is a selection of those. As I said in a talk last week at a conference, one reason we select them is because they're pretty. And every amateur will, at some stage, take a picture of at least one of those. So we can run some kind of poll in the audience, and I doubt anyone who has ever taken an astronomical picture will not have taken one of any of those objects. And all we really want is you can make as many pretty pictures as you like. We want the data. And this is really what we are after to do the science exploration for that. So it works quite well. We have now more than 70 people who take part from 12 different countries. You can see where all the telescopes are on the map. There's one or two outside that region, but in total, we're now getting closer and closer to having collected 40,000 images of our targets. It's about the same as having 700 hours of exposure time on a 1 square meter mirror telescope. That's how much data we have collected. And in total, we've almost measured 160 million brightnesses of stars now in all the images. This is just to show you that over time, this tells you how many pictures we had at each time. So we all have seen a lot of exponential functions in the last year. It's almost like that. So we're still growing, and we're trying to get more participants to really achieve that goal of 1 picture every day or two pictures every day for every target, in every filter to really really achieve that target. We're still quite a bit away from that. And remember, we want to do this for about 25 years. For long-term purposes. That's one example near the Christmas tree cluster from Mark Shelley. These are just 3 pictures he took over 3 months. And you can see there's a lot of these stars, and most of them are young stars that change their brightness. So you can circle them to highlight the ones you can see with the naked eye. There's the really bad one that just disappears completely in one picture, but all these other ones, they all blink to some extent. But what we do is really, compared to many other projects like AAVSO or things like that, we will measure the brightness of every star in every single picture and store it, because you never know which star suddenly starts to be variable, and then you have basically its past behavior. Okay. So now let's show you some examples of what we have done. There's this particular star in the Pelican Nebula, which I think is, where is it? Here, that's the one that we had a closer look at. or a PhD student or a master's student had that. So the first thing that I plotted here is the light curve in the visual, or the green, the red filter and the infrared filter, over about 2 years that we've taken only with the University of Kent Observatory. It's only our data. So you can see Kent is reasonably sunny or clear, whatever you wish. So we get quite a large number of nights where you can observe the target. And what you can do from this data alone, you can kind of see there's dimming events. And if you do the analysis properly, there's a period of about 31 days, roughly a month, where you get these dimming events. But they're not all the same. So each dimming event looks different. So there's an occulting structure in the disk which moves in front of the star roughly once a month. And then goes back out again. But this is only the data from our own telescope. And then we asked all the participants for a couple of weeks in 2018 to observe this field every day, every night, as often as they could. And then you get these light curves here. So this is now just how much is it? About 50 days. And there's more data points in those 50 days than we had in the 2 years with our own telescope. So that really shows you how much more detail you can get. This is just one of those dimming events that we have now really resolved. And you can see really changes in the amount of dimming on a even half-night basis. So there's very, very small structures that you can really resolve in that material, in that object. And what the student has basically done is you can measure, because it comes back every month, you know how far away from the star it is. So you know the velocity it's moving. And you can hence calculate for each of these events where it shows up, how much material do you need to explain the data? So how much mass is there in that occulting structure every time it comes back? And you can see it varies quite a lot from dimming event to dimming event. And it's actually not a lot. So you only need 0.03% of the mass of the moon in that structure to cause these effects. But we know the material is moving in and out of that structure very, very quickly. So there's a lot of stuff going on in these inner disks. There's a lot of movement. It's not a static thing that just keeps going around and nothing happens. So on very short time scales, so from here to here, this is just a month, this structure had almost no material in it, and then it filled up to this kind of almost maximum that we have found in any of the events. And the same is true the other way, right? You had one where it was almost full, and then the next time it came around, all the material was gone. So what we think we have is a warped inner disk. So you have a star in the middle, and the inner edge of the disk is warped upwards on one side and down on the other, and we're looking from one side. So if you look from this side, the warp is on the top, kind of blocks the light. The object appears dim. If that structure rotates by 180 degrees, you're seeing the star directly, and the object is bright. And typically, these objects are explained by magnetic fields and the rotation axis of the star being misaligned with the disk. Now, we know from the period that that structure is about 15% of the astronomical unit away from the star. And it's basically impossible to do this warping at this distance with a magnetic field from the star. They're simply too weak to do this. So you need something else to keep the structure in place or to repeatedly put it there. And the only other thing except magnetic fields is gravity to do this. So what we think we have in that system is there's a planet somewhere in that disk that is inclined to the main disk. So its orbit is somehow inclined. You don't need a lot to do this, and a lot of inclination. This is completely exaggerated, so you only need a handful of degrees. And what that planet will do with its repeated gravitational pull, it will twist the inner part of the accretion disk. Everything that's inside its orbit will be twisted into the same orbital shape. So there's a lot of people have done a lot of simulations on that, and we are simply seeing that system somehow from a direction like that. So we think there's a forming protoplanet somewhere in the inner disk. We don't exactly where it is. Has to be reasonably close to where that structure is forming, but we can't. There's no direct way of detecting it. But that's the only sensible explanation that's left after ruling out all the other ones that could be proposed for that. Now let's have a second look at this region and a second star, this object with this telephone number here, which sits over there. So this region is great. There's a lot of really strange and interesting objects in it. And what we've done for this object, we did a periodic analysis. So this is the light curve in the green, looks just flat with a lot of noise. But if you actually carefully analyze it, what you find is that object has a periodic signal in it of about 20 hours. So 0.8 days or just below that. And if you make a face folded light curve, it looks like that. So almost a nice sine function. And it looks like there's a lot of scatter. And what you will find is the majority of that scatter here is actually a change in the amplitude of the modulation of the signal over time. So the amplitude basically changes over time. And that's why if you take all the data and you make it face folded, it looks quite noisy, like you have bad data, but that's not the case. So what we have hence done is we simply measured the amplitude of that sine function as a function of time in our data. So this is about 4 years, and this is the amplitude in magnitudes that you get of that periodic sine signal. And what you can see, so the colors are the different filters. Initially was reasonably large, 7–8% of the brightness, then it dropped, then didn't do much, then it increased quite a lot, so by 10%, again went down, and then slightly up again. So you can see basically spots on the surface of that object which change temperature and size. And because we got 3 wavelengths, we can basically model, we know the temperature of the star, so we can model the spectrum of the star, and then we can model a spot on the surface which has a free temperature and size, and simply see which size and temperature as a function of time explains the behavior that we can see in the amplitudes. And that's what the next graph kind of shows you on the top. This tells you the temperature of the spot that you have. The bottom gives you the size of the spot as a fraction of the total size of the surface area of the star that you can see. And the star itself is about 5,000 Kelvin. So the spot is slightly warmer than that. And you can see over time its size, again, it drops, then it gets bigger again, it drops again, and so forth. And there's still also some measurable change in the temperatures with quite some uncertainty. So we have now, I have a new PhD student who's systematically really going through all the objects to really study how often do they change their brightness, how often do they change their size, and does that somehow depend on, let's say, the rotation period, their age, if it is a really hot spot or really a cold spot, and so forth. So we've already started this. So in the Pleca Nebula region, there's 40 objects where we have already identified rotation periods, and then for the next year, the PhD student will hopefully go through and do all these modeling and these calculations to really study these objects in more detail. And then this is the last example that we have. I call that the weird one, because 3 years ago, about here in time, I asked a former PhD student who was just doing classification of shapes and weird math things. I gave him all the light curves that we had and told him, give me the strangest light curve that you can find. And this object popped up. And the reason it popped up was all the stars that when they change their brightness, when they get fainter, they turn red. Right, so typically they get fainter because you put dust in front of it that will change the color to red, or they get brighter because there's a lot of mass accretion going on, but that is a very violent process, and that typically generates blue light. So literally every single star that is variable in the survey at this stage, when it was faint, it was red. When it was bright, it was blue. This one was the other way around. And I had no idea what this could be. So we have taken some spectra of this object and really kind of made sense of what that object is. What this actually is not a young star in that star forming region that we're looking at. It's a massive young star, so a spectral type B star, so about 6 times the mass of the Sun, which is young, but it's at 18,000 light years from us in terms of its distance. What we have done is, during some of those eruptions, we've taken some spectra, and I've also told the student, okay, we have no idea what this is, but you can model the star, and you can try to model these outbursts by saying, okay, I put some kind of explosion on of a given size and temperature, and you try to model how hot does this explosion have to be, and how big does it have to be to actually mimic the light curve when you just leave the star alone as it is. The student has done that. So this is just a zoom in into the 2 last of these outbursts. What the student has done is, in red, this is the temperature of that additional explosion that you need to explain the light. And in blue, this is the size that object needs to have compared to the size of the star. So 1 here is the size of the star. So that explosion basically at the peak of the outburst here is about 5 times the size of the star in surface area, and has a temperature of about 6,000 degrees. Initially, it's very small, but much, much hotter. All the explosions, they have a similar pattern. They start off very hot and very small, and then they cool down to about 6,000 Kelvin at the peak of the brightness. And what you can do with this is quite interesting, but I'm going to explain to you that after I show you one of the spectra. So we've taken a spectra here of the hydrogen alpha emission line. So this is a red line that comes from atomic hydrogen, which is surrounding these young stars, right? You got that massive star in the middle, hot, 6 solar masses, you got this disk around, and it's actually what we can call an explosion is a mechanism in that disk. So this material in the disk that is moving inwards rapidly and accreting basically material, which causes the disk to heat up and make the whole object get brighter. And if you look at the spectrum of the emission line, so typically you would expect a single wavelength peak where the hydrogen alpha emits, but the hydrogen alpha emission comes from the disk, and the disk is rotating with respect to the observer. So you would expect the emission to happen at the actual wavelengths where hydrogen alpha would emit, but because it comes from the disk, some parts of the disk, they move away from the observer. So that part is redshifted. So that part that is moving really fast away from you gives you the right-hand side peak in the spectrum at slightly longer wavelengths. The bit on the other side that's moving towards you, that is slightly blue shifted, that explains the peak on the left. And what you can do is you can simply calculate from the difference in wavelengths, the velocity at which the material is orbiting the central star. And it turns out to be 150 kilometers per second. With that, you can work out how far away is it from the star, because we know from the spectrum this is a star of about 6 solar masses. So we know it's about 10 times the radius of the star away. So what we know is there's this kind of ring of material that is lighting up. And we know the increase in brightness. Right? We have modeled that as with this simple model of an object that just has a temperature and a given size. And from that information, you can actually work out how much material is falling onto the central star, because its potential energy is converted into the light that you see. And you add that all up during one of the bursts. And what you find is each of these bursts roughly accretes 1 Earth mass of material. So I was quite surprised. But then if you think about it, it's actually not a lot. You might even expect these things to accrete at a higher pace, because even if you do this constantly over 1 million years, you only accumulate one solar mass. Right, because the Earth is roughly 1 million times the mass of the Sun. So these bursts basically add about an Earth mass every time they happen to the mass of the star. And because we have this very good resolution, you know exactly how the material is moving at what speed. Right, so that's another way of really looking at the details of these disks very close to the star, because most of the material we know from the spectrum here sits within about 0.1, 0.2 astronomical unit from the star. Remember, the star is much bigger than the Sun, so that is easily about 3 or 4 or 5 times the size of the Sun. So that's basically what we can do as well. You can find these weird objects and then spend a couple of years trying to find out an explanation, or find an explanation for them. And lastly, a couple of words how it's in principle possible to participate. We have a website. The address is on the last slide, which has a list of targets and has some instructions which you can read. But in essence, you can observe any of the targets in any filter, any exposure time, any field of view you like. The only thing that is important is that your pixel scale should be below 3 arcseconds, because many of the fields are very crowded, and then photometry merges stars together and does become less useful. The only thing we require you to do is a flat field and dark correction, and if you have more than one image per night in a given filter, just stack them together, because we're not interested in kind of very short time scales. Day-to-day observations is really what we want. After that, we have a web server where you can literally drag and drop after getting a login, drag and drop your FITS files, and you upload them. Then there's a little bit of processing to do, which we are happy to help if you have a lot of images, or I will tell my students to be happy to help you in that. And what it basically does is we ask you what target region is it for, what instrumentation have you used. So that's a single setup, and then you can just select, if you have several telescopes in particular, which data is taken with what telescope. And then we simply run an astrometry.net solver over it to find all the positions of the astrometry. We do a basic source extraction to find all the magnitudes of all the stars, compare them to reference catalogs, and then you simply check if the photometric calibration has been done correctly, or if it included some saturated stars, things like that. There's a lot of help videos available. So once you've done this once or twice, it gets very, very easy to do. And after that, as soon as you accepted the data and said this is all fine and calibrated, it's in our database, which is publicly available. So you can extract your own data as a search function. You can look at the light curves if you want. There's a download button at the bottom. You can extract the data. We started to put some kind of analysis videos on where you can basically learn how this all works. Or if you're looking for periodic ones, you have a nice period analysis Jupyter notebook available. Even if you don't speak Python, you don't need to, you just press enter and it will do everything for you. But you can see basically, is your object periodic, what's the amplitude, what's the period, and so forth. And you can just play with the data any way you want. And at the end of it, the reason we're doing this is science, so we're writing papers, and we will put your name on a paper. The vast majority of all these people on that author list are people who have delivered data for the project. So there are some papers where we don't include every participant, but the idea is basically once a year or every year and a half, we write one of those kind of survey type papers where everybody whose data be analyzed or used for that will be a co-author on the paper. They're written in public, so you can see the whole process, basically from the start of the writing all the way to the end. we might ask you to write a little bit about your observatory, small paragraph, so that we can show where the data really comes from. But you can basically participate in the whole process, learn things about the science we're doing, as well as actually helping us at the same time. So that's it from me. That's the website, easy to remember. We also have kind of social media accounts if you're after. So all our help videos, they're all via YouTube, but they're linked from the server, so you don't have to really search on a channel. But if you want to stay up to date, then the website or the social media is the best way of doing that. Thank you.
Dirk, thank you very much indeed. That was really very interesting. Really very interesting. I think I could manage that sort of that imaging schedule. Any target, any filter. That's kind of how I. Anyway, let's move on from that. Okay, I'm going to open up. The chat has been very quiet actually, so people have obviously been paying attention. But does anybody have any immediate questions for Dirk?
Can I jump in first? Thank you very much.
Go on then. Yeah.
Quick one. You say any filter. Does that mean that there's some filters that you're not getting as much data for? Because I'd imagine most amateurs will be using, particular filters. So is there kind of gaps in the data where you could use more input in those filters?
Yes, but the amateurs won't be able to help with that. So it's the ultraviolet and the blue. So anyone who's tried that, even tried to buy an ultraviolet filter, will know it's all the detectors are not very sensitive. You need a big telescope to do that. And the particular problem with all the young stars is they're all very red. So they're not very bright in the ultraviolet. So the shorter wavelength filters are a bit rare. Most of our data is literally visual red, infrared, and blue. So hydrogen alpha is always welcome. There's not that many because, again, you need a larger exposure time, maybe a larger telescope to do that. So these are the filters that we accept in the sense that anything that is roughly one of those. So it doesn't matter if you got a DSLR with a tricolor filter sit in one of those biofilter things, or you have a CCD or a CMOS camera with specific filters. So any of those will be acceptable. So what we will do is, if you got, let's say, a DSLR color camera, right, you get a blue, a green, and a red filter, and our software will simply calibrate that into a B, a V, and a R. And because we have all the brightnesses of all the stars in all the pictures, what we are able to do is correct for any color terms between the different filters. Because we know from, or at least we can run a query for every region, we know which stars do not vary. So we know exactly what their brightness and their color is. And we use them, we identify them in each picture and simply correct the brightnesses of all the other stars to make sure that these color terms are corrected for. So as long as it is a filter, we don't take any unfiltered images. As long as it's a filter, it's something like UVVRI or H alpha, then we will take those and calibrate them.
And will you take, because I'd imagine a lot of people have got old data that matches those parameters on their hard drives. Will you take?
Yes. So you might have seen that on that very first on that one slide where I showed you how much data we have. That one, right? It says here, the HOYS project starts. We've already accumulated some images from before. Right, so these historic pictures are good. In particular, if I go to any amateur society, I go to the website, all our targets are there on their picture gallery. Right, so we want also these old data. In particular, you can see the kind of growth of images at the beginning of the project wasn't very good. So these old pictures are good, right? It just helps us to understand what these objects have done. So in particular for these, for that research where we look at how do spots on the stars evolve over time, right? Every picture is very helpful in the past because So the more pictures you have, the more accurate you can measure the amplitudes, and hence infer the temperatures and sizes over time. That's really what we try to do.
So we should all have a delve on our hard drives.
Yeah, everybody is welcome to do that. Yeah.
There we go. So that answered Andrew's question. DSLR or color CMOS cameras. That's fine. Come on, Steve, unmute yourself then. Ask your question.
Yes, think I've done it.
Yes, well done, well done.
Yes, thank you. Stacked or raw data?
What do you mean by raw?
Individual sub exposures.
Yeah, I think I mentioned that. So we want, if you take more than a single frame per night, please stack them all up. The reason for that is it gets rid of things like individual cosmic rays better if you median average things.
Yeah, no use cloud.
And we are not interested in these kind of hour variations. So it's kind of 12 hours is kind of the minimum gap that we want. So if you take 100 frames in a night, please don't upload them all separately, because then we might actually start refusing to help you with the processing as well. There's some data sets where people uploaded a whole night of individual 5-minute pictures, which is quite interesting for some objects. You can start seeing variations as well, but so we want them stacked for each night in each filter.
And calibrated as well, Dirk. I think I did see, did I not?
Yes, if by calibrated you mean a simple flat field and dark, then yes, yeah. Everything else, that if you solve the astrometry, something is not necessary, we will wipe this out. Not because we don't trust you, but we want all the pictures be done in exactly the same way. So we use the same software to solve the astrometry for every single picture, and the same source detection for the photometry to have more consistency.
Yeah, that makes sense. So actually, so those of us that do try and take pretty pictures, we haven't got to do anything different really, apart from send our data to you.
Yeah.
That was basically what I was asking. Yeah, because I don't take hundreds of, well, I do if I'm doing solar or planetary, but not deep sky stuff.
No, but that's but that sounds yes, that sounds like a pretty straightforward thing to do then. So as you know, providing it's clean data and we've calibrated it, we can upload that and actually make a contribution to a project.
Yeah, well, one thing I didn't say is it's the ideal filler for other things, because even in 10 minutes you can take a useful image, or several even. So if you're interested in doing things like exoplanet transits, right, you need a whole several hours of clear sky. That's much more tricky than, you know, maybe 15 minutes for one of the targets. So it's a very good filler project as well. It's something you can do with more time, because even a single picture is useful.
Yeah.
The only thing in terms of strategy, if you want to invest a bit of time, let's say you have a half an hour, what we recommend is that you try to observe a target in multiple filters instead of a lot of targets in the same filter, because the most important bit that we are after is the colors, because most of our research relies on the colors. So it's much more useful to have a full set of wavelengths or filters for a particular region than let's say you have 4 filters, BDRI. So it's more useful to take all the filters for one target instead of four different targets in one of the filters.
Okay.
For the scientific exploitation. Of course, I will not prevent you from doing all the targets and all the filters.
So you mentioned about saturated stars. Does that mean you reject the whole frame, or do you just reject the stars that have reached saturation in
No, so the way the processing works is that's the only thing that we haven't yet managed to completely get automatic, where we ask the users to check, and I check this in the background as well, is we basically, the program is trying to guess which stars start to be saturated or in the nonlinear part of the CCDs. So all the brightnesses are measured, even of the saturated stars. And the user simply selects the range of brightnesses where the saturated or nonlinears are taken out, and also where the calibration gets too noisy. Then in the background, all the data is stored, but these objects which are then flagged as too bright or saturated, there's simply a flag somewhere. So if we do analysis, we pull out all the data and then we remove basically everything that gets flagged or has an error that is too large, things like that. Because for example, if you look for dimming events, which are 2 magnitudes deep, it doesn't matter if you got 20% errors on your brightness. But if you want to do rotation of stars and you want to measure the amplitude of one of those sine functions with an accuracy of 1%, then you only include the high accuracy data. Right, so even if you have a small telescope or short exposure time, the pictures will be useful for one of these science things at the very least. So basically, every time we pull data out, we then quality check them for the purpose or for what we are doing. Right? If you need high accuracy data, then you take all the big error bar ones out. If you look for variations of 2 magnitudes, then literally every point you can use. So even the pictures that seem to have been uploaded without any flat field, they're still good enough.
Norman had a question, Darragh, that you...
Sorry, Norman, I must have missed that one. Apologies.
The question is, do you take spectral data?
No, but so simply, so the project is really set up to look for, monitor the brightness, photometric brightness monitoring. So we already had 2 years ago, there was someone who was building a spectrograph on his telescope, so if you do that, we are quite happy to kind of see if we can monitor some of our targets, because that's a 1 star by 1 star approach, and see basically what we can do with that. So that's one of the reasons we monitor hydrogen alpha, because that or the ultraviolet light tells you about the accretion rates, so how much material falls on the stars. Both of those things trace that. I'm actually looking for money from the university, so that's more or less a joke, to get a bigger telescope with a spectrograph to do exactly that. So if there are people out there who have a spectrograph, then we can see what we can do, which, we need to have a look at limiting brightness and what kind of objects we look at, obviously the bright ones. But that is certainly something we can do as a spin-off. But at the moment, we don't really collect that as such for the project.
Yeah. Since you look at dust clouds, I mean, isn't a measurement like anisotropy going to be useful as well?
How do you mean that?
Well, you've got a scattering effect that goes on, and
yeah,
obviously that will bias between the left and right polarizations, so you can
yes,
extract more data from what's going on.
Yeah. Again, that is something that's probably requires quite a big telescope, because these stars are still faint, right? We're talking at 3,000 light years, the sun is a 15th magnitude star. So if you want to do polarimetry, in principle, yes, you can do these kind of things. But I'm pretty sure you need a decent telescope. I don't know what you have in your back garden, but
only a 12.5 inch.
So yeah, but in principle, that's one way of identifying these or scattered light things is by looking at a polarized light. So you can filter out the real light of the star, even if it's completely scattered and changed in brightness, because the polarized light that gets to you, that's the one that's coming really from the star. as you can saw, that you probably saw that in the HST pictures, right? So the polarized light, where is it? So that scattered light here, so that is linearly polarized on both sides. So here you can almost see it in the broadband because there's quite a lot, there's no other light. But the polarized light will basically, if you take a spectrum of that will tell you how the star looks, which you can't see because it's hidden behind the dust. So yes.
So either win the lottery or move to sort of amateur interferometry.
Yeah, I mean, spectropolarimetry will do. So you basically get a spectrograph and put that through a polarimeter to basically take a spectra of the polarized light. That's kind of what you need to do, but you need a 10-meter telescope really for most of these kind of objects.
I'd like to order one, Grant.
It will come in bits though. You've got to join it together yourself.
Don't pass it in the mirror.
Is it? Would it be like one of those magazine subscriptions, Grant? Would you pay £800 a month and you get a little bit every now and again? That's
can I ask another question? Apologies. This may be one of those things that all you guys say, oh no, that's not how it works. But do binary stars accrete together out of a single accretion disk, or can they? And if so, is that something you can detect with the method you're using?
Well, with binary stars or multiple stars, you can basically get whatever you want. You probably know most stars are in binaries. The simple way to explain this is that angular momentum I talked about before. So where these cores, when they collapse very early on in the process, so the angular momentum problem occurs also in the initial collapse. And one way nature gets rid of that is it splits the core in two. Both cores orbit around each other, and that kind of soaks up most of the angular momentum. And that's why you get so many closed binary systems in nature. But what we know is from investigations of objects, young objects with disks and multiples with disks, you can get basically every combination that you can think of. You can get a closed binary, so really orbital periods of way less than a day, which have a circumbinary disk, where basically the material accretes onto both stars in the middle. You can get binaries which both have their own disk. So they're slightly wider because the disk will only have a maximum size. Because if it gets too big, it's going to be disrupted by the companion. So you can get binaries who both have their own disk. Some of these systems then have an additional circumbinary disk around that. So you get literally everything you can imagine will be out there. You just need to find it. It only depends basically how wide the binary orbit is what you can do. So for example, this last object that I showed you, that one, we can clearly see the signature in the emission line from the disk, and we know from the calculations that the material that we see emitting is I think 0.2 AU or 0.3 AU from the star. What I haven't shown you is we have a second spectrum at a different time where the object was faint. You still see the same structure, so the disk is still bright at that stage, but what has changed is that the gap between the two peaks here actually has widened a bit, which means when the object is faint, the material that you see glow in H alpha is actually closer to the star. That's one thing. But what we also see is the whole line has shifted a tiny bit, which means the whole star with its disk has changed its radial velocity towards us. What it means is it's in a multiple system. So the light we see when we see it faint, there is a companion somewhere. But that companion has to be very far away because otherwise the disk wouldn't be there. Right? We can already say that. So we only have two data points. So there's a shift of about one angstrom in the position of the line. which is a handful of kilometers per second in the change in velocity. So you need to monitor this over a couple of more months or years to see what the orbital parameters are. But that object is clearly a binary. Most massive stars are binaries. About 2/3 of all the normal stars, like the sun, are in binary systems. For the massive stars, they're literally all in binary or multiple systems. That is something you will find out. But in the photometry, unless you get regular eclipses, which will be like clockwork, we can't tell if it's one star or two in that system. You can tell by looking at the Hertzsprung-Russell diagram, where you have the main sequence of stars. You simply look, where is that star? Now with Gaia, this is really nice. That's one advantage of all the targets. They're so bright and they're so close. We know exactly where they are with Gaia. And what you can do is basically look, is the star on a sequence. The young stars are of course not on the main sequence. There you can't tell, right? Because they're above the main sequence anyway. So because they're bigger than a star on the main sequence, so they don't fuse hydrogen yet. But for main sequence stars, you can tell if they sit above the main sequence, because that indicates there's two stars contributing to the light. But for the young stars, it's very hard to do, unless you take a good spectrum and try to see, is this one star or two? But if they have very different masses, it gets very tricky, because the light is really dominated by the bright one at all wavelengths. It becomes very, very tricky to do.
Can I ask another question, which might be stupid? Apologies, but
yeah, I know, stupid questions.
Can you get an older star that still has an accretion disk left, or will the accretion disk always end up either on the star or in planets?
Again, whatever you can imagine will probably happen. So in terms of the formation, if I go to the cartoon again, right? So the accretion disks, we basically know from statistical arguments. You basically go to young clusters and you count based on the age of the cluster, which you can model by looking at the where the stars are in the Hertzsprung-Russell diagram. And what you then can do is you can count how many stars with disks do you see as a function of age. And what you see is typically after 5-6 million years, the disk fraction drops below 50% or below 20%. So clearly these disks only live a short amount of time. What you get later on, so after 10 million years, the accretion disks are gone, which means most of the gas is gone. There's no real accretion going on anymore. But these planetary systems are still at the very beginning of their evolution. Right, you get these protoplanets and hundreds of thousands or millions of smaller things floating about, which collide with each other. Some then get accreted onto the big planets, fall in the star, gets ejected out. But what happens very often, if two things of equal mass hit each other, you make a lot of debris. And you get these objects with so-called debris disks, again, which is basically a still forming kind of planetary system where things have gone wrong or haven't finished yet making the big planets. So you get these kind of systems. They last maybe for a couple of 100 million years until everything has nicely settled down. And then again, you can kind of rejuvenate these disks. You can just have a normal main sequence star that just happens to, in its orbit around the galaxy, hits one of those cores and hoovers up new material, right? So it's quite unlikely, but it's not impossible to find these. Typically, once the disk is gone, you might not kind of revive it in that stage to get these accretion disks. But you can have a binary system, happily living for billions of years, and then one of the more massive star becomes a red giant. That will feed a lot of material into the system, which might or might not settle into a disk. right? And then it might become one of those cataclysmic variables, all sorts of strange objects. But again, you can basically make that disk around a main sequence star after a couple of billion years, right? Nova are the best example. Cataclysmic variables are the ones which are basically things with a disk, but old. So stellar evolution is very interesting. It's also a nightmare because there's so many things that can really happen.
Yeah. Okay, good question, Grant. Norman again, another one from Norman.
Obviously, we got the Vera Rubin telescope coming online. How's that going to affect your data collection? Is it how much extra are you going to get from that?
We personally, not much. So we've been very careful trying to avoid competition, which was very easy with, I still call it LSST, it's easier. So most of our targets are in the north. So we have summer and winter targets. All the summer targets are in Cepheus and Cygnus, which of course you can't see from Chile. The winter targets are in Orion. But the way LSST will work, you might know that they're going to basically try to scan the entire sky with that 8-meter telescope, and they will still have a lower cadence than we do. That is fine. The main problem is they will run this with 15-second exposure times. So the minimum exposure time is 15 seconds. Because if you do any shorter than that, the data flow gets ridiculous. It's bad enough the way it's set up. You can do this on the back of the envelope, but in 15 seconds, a 8-meter telescope is going to saturate every star brighter than 15.5. This is so our data typically goes between 10 from the saturation to about 16 or 18, depending on what we do. So that's the first thing. So we will get some useful data for that. So which in terms of the science will be good. You will be surprised, our cadence is still much better than the LSST will be, because most of what they will do is away from the galactic plane, because so that they were even so the strategy for the observing still not really set. Their initial idea was that they're going to do the whole sky for 10 years as often as they can, but that excluded the galactic plane, where all the interesting stuff happens, in my opinion, because that thing was built for supernova, right? So what they said was basically, if we keep repeating every couple of days in the galactic plane, after 1 year, we can't get any deeper, simply because you reach the confusion limit. Basically, the stars get so close together that you can't get any deeper, which of course, if you do time series astronomy, is a stupid argument. I don't want to go deeper. I want to know what happens in the other 9 years. So it's still unclear how they will run this, but we might only get 1 year of LSST data in the galactic plane, where there's simply too many stars for them to cope. And the main problem is the saturation limit is 15.5. And my argument is, and that's one reason we selected things closer than a kiloparsec. If you find something interesting, we're looking for these big outbursts, then I can take a 4-meter telescope, which I can reasonably quickly get hold of, put a spectrograph on it, and analyze this object to death. If LSST finds something at its limit, which is 25th magnitude, then you first go around and try to collect a lot of money to build a 30 or 100-meter telescope to actually follow this up. Right? That's one big problem, that there's no 30-meter yet online. There's 2 that are being built. LSST is going to find a couple of million transients every night, right? Which won't follow up. You can't do that. So it's very difficult. So I don't see it as a competition. It's nice supplementary data.
Oh, yeah, data deluge, but mainly in the southern hemisphere.
Yeah. So basically, once that comes online, no one is going to look at the northern hemisphere anymore. The same, the big 30-meter from ESO is going to be in the south. If the Hawaiians keep protesting, the northern hemisphere one will probably never be built. So it will be very tricky to do things in the Northern Hemisphere because all the big sites, the SKA, same thing, the big radio square kilometer array, that's going to be in the Southern Hemisphere. So there's a lot to, be done in the Northern Hemisphere.
Thank you.
Thank you, Dirk.
Okay, good stuff. Well, Dirk, I think you've answered pretty much everybody's questions. So excellent. Yes, thank you very much indeed. Really,
I could carry on asking questions all night. Really pleasure having yourself here, Dirk, to be able to ask such questions. And apologies if mine are stupid, but it's really, really interesting to hear your answers. So thank you.
I think it's great as well that there is an opportunity for us as amateur astronomers to get involved in some of these science projects, and especially if we're not going to do anything massively different to essentially what the bulk of us already do on those rare clear nights that that we do get. So I think that's something we should definitely follow up, Grant.
Absolutely. I'm pretty sure from the Spanish observatory we've already got a heap of data that we could push through for some of these targets, because as you say, they're the pretty picture targets that everyone goes after anyway. So yeah, stuff's
there. May as well use it and get our names on some scientific papers. That'd be something.
We don't want to drag the papers down too much.
No, indeed. Dirk, that was absolutely brilliant. Many thanks indeed. I think you deserve a very large cup of tea after all that.
I'll have a beer, I think.
Not one for dry January then. That's good.
No, I got lectures tomorrow, so I need to be able to cope. That's not recorded anymore. Oh, it is. Oh.
No, indeed. Grant, next week we have a speaker lined up.
We do. We've got Keith Townsend next Sunday coming to talk to us about the Messier objects and a little bit about the history of Charles Messier and how he found them, and then looking at also the Messier Marathon and how to go about spotting them all. So that should be interesting. Yeah.
That will be really interesting. He's a good talker, is Keith. Absolutely. Yeah, we look forward to that. Rightio. In that case, then everybody stay safe. Enjoy your week. Let's hope the weather doesn't close in too much more. Night, Graham. Bye. Okay. So take care, Dirk. Many thanks again, and we'll see you all very soon.
Thanks, Darren.
Yeah, thank you.
Night all.
Bye.